Hi, welcome to 2.5 Stretches of Functions. In this video, we're going to learn two types of new transformations that correspond with a parameter a and k. But first, we're going to recap what we learned so far. So just a quick overview. This right here, I'm just going to highlight this. This general function tells us all the different kind of transformations that we can do to a base function f of x. Okay, f of x is always our base function. Maybe, let's just say it's square root of x. So all this does is tell me all the different kind of transformations that we can do to f of x. So this in and of itself is not an equation, but they're instructions on what we can do to the base function f. Okay? So far we've learned that two of these, d and c, those correspond to translating the graph f of x. So there are horizontal and our vertical shifts. So you will always see d inside of a bracket with x, okay, before the function is processed. So maybe it looks like this, x minus 5. That's an example of d. So if d is greater than 0, then our function is supposed to shift to the right, d units. And if d is less than 0, then it's going to go to the left, d units. Our other translation is c. This is always what's added after the function. And if c is greater than 0, then we're going to shift up c units. If c is less than 0, then we're going to shift down. So all of these translations don't change the shape of the graph, they only change its position. After that, we looked into reflections. So there's two types of reflections. There's one where we multiply the base function by a -1. And what that is it reflects the function along the x-axis. And if we replace x with -x, that's another reflection that reflects along y-axis. Okay. So that's a quick recap of the two kind of transformations that we've done so far. Today now we're going to look at the two new ones that have to do with a and k. So if you notice, a and k kind of represent the negatives that are in here. Okay. But now we want to talk about what happens if we have other numbers. So like 5 or a half. How does that affect the graph? So first, we're going to start with an investigation that you guys will do on your own. It's going to be on page 113, 113 and 114. Okay, so go ahead and perform that investigation right now. There's about a total of, we got 4 questions for the first one and then 5 for the second one. Okay, so if you want, you can pause the video right now. When you return, I won't be taking up the investigation. We're going to do that in class, but I am going to continue on with the lesson. Okay, so if you want, go ahead and hit pause and do that investigation, and I will see you when you are finished. Okay, welcome back. So we're going to get into the rest of this lesson. So we're going to recap some of the things that you would have seen in investigation 2 as well. So here we have a base function, f of x. Okay, it's just a parabola. And there are 2 other functions that have been created from the base function f of x. So we created a new one called g of x. Okay, and this would be when we take a value of a and we multiply it by the function. So it says if a is greater than 0, we're going to see this graph stretch. The blue one's going to stretch and turn into the green one. The reason why it's stretching vertically is because we're multiplying the output by something. So f of x is a function, and when you plug in numbers for x, you're going to perform an operation and get an output number. Well, then when we multiply that output by a, what it's doing is it's multiplying it by the a value. So our points end up getting vertically stretched. Okay, so it's kind of like multiplying the graph by a scale factor. If you think of a as a scale factor, it starts to make sense how this graph starts to stretch. So we can summarize a bit here. We can say if a is greater than 1, the function is vertically stretched by factor a. So whatever the value of a is. So if the number in front of the function is a 2, all the y values get multiplied by 2. So what this does is it takes any point, x, y, and it turns it into a new transformed point, x comma ay. All right, and just something to keep in mind with this, if a is greater than 1, we want to be using the words vertically stretched. Okay, that means the function is going to grow, and it's going to, when it gets multiplied, it increases in size and it gets stretched. Okay? Now, if we have something between 0 and 1, so if a is greater than 0 and less than 1, well, then we have what we call a vertical compression. So we'll say the function is vertically compressed by factor a. So if our value of a is between 0 and 1, so like a half or 0.2 or 1 over 5, then we can say it's vertically compressed. So an example of this would be the red one right here, this red function. Okay, the blue one was our base function here, and when we multiply it by a, which is smaller than 1, between 0 and 1, then the graph shrinks and our points move down towards the x-axis. And we call it a vertical compression because it looks like we compressed the base function down. Whenever you're using the word vertical compressed or vertical compression, the factor a needs to be between 0 and 1. Okay, now to summarize the value of k. So k is always inside with the function. And if k is greater than 0, okay, we're going to have a horizontal stretch or compression of the base graph f of x by a factor of 1 over k. So we'll explain how we get this 1 over k in a second. First, let's look here at our base graph root x. So we can see here in the green graph, if we put in a value for k that's bigger than 1, so like 2 or 3, if we plug that in here for k, what happens is the graph, you might be tempted to say it's a vertical stretch, but it's actually being compressed horizontally. So if you think of it, if we take that base graph and we compress everything this way, well, the blue graph starts to turn into the green one, okay? Because a point that's, let's say, right here gets compressed over to this point right here. And this point gets compressed over to this one here. So what we're doing is we're actually multiplying the x values by a scale factor, and that's actually going to compress them. Okay. So you might say, well, if k is 2, when I multiply it by 2, wouldn't it make it get bigger and bring everything like this way? Well, no, that's not how it works. So I'll show you why it doesn't work that way in a second. So we'll just say if k is greater than 1, the function is horizontally compressed by factor 1 over k. All right, so when you see k greater than 1, you want to be using the words horizontal compression. Now, if k is between 0 and 1, the function is horizontally stretched by factor 1 over k. Okay, so I'm just going to give you a quick example of why these are the opposite. So if we were to plot the function y equals x, we would get a nice graph that looks like this here, like y equals x. Okay, call that y equals x. If I then ask you to graph y equals 5x, well, what kind of values would you have to put into x in order to get the same output as this function? So if you put 1 into here, what I mean is if you put 1 into here, you're going to get the 0.11. So if I put 1 into here, I'm going to get the 0.15. Okay, that's showing like a vertical stretch. But if you think about it, if you put in order to get the same y value out, because this is a horizontal stretch of compression, that means the y values stay the same, only x excuse me, only x changes, then we would have to put in something like 1 over 5 in. Okay, if I plug in 1 over 5 into x, then I actually get the point 1 over 5 comma 1. So notice, to get the same y value, to get the same output, I had to put in something 1 over this value in. Okay, so what that would do, it is actually take the 0.11, which is here on the graph, and squeeze it over to 1 over 5 comma 1 over here. Okay, that's essentially the idea with the horizontal transformations. So because we're changing the value of x in the function, like inside the function, we have to compensate for it with the values that we put in. So those values are always going to look like the reverse of what's happening in here. So here we have 5 times x. Well, we put in something 1 over 5. So whenever you see k between 0 and 1, you want to use the words horizontally stretch. Okay, I'm just going to erase this here. We don't need this.